Hello everyone, welcome back to our fifth lecture on the K-means algorithm. And this is a very special lecture just because this is our first introduction to an unsupervised machine learning technique. And before we actually get started on K-means, I would like to first recap what we have done so far in our previous lectures. So far we have dealt with two big processes. So first we dealt with regression, and then we dealt with something called classification. So just as a quick summary, regression was the process of predicting a numerical output based upon a, thank you. All right, so regression was essentially the process of predicting some numerical output based upon a certain number of inputs. So essentially what we did is our example was we used test scores as an example. So our inputs, when we actually implemented this in Python, were the SAT writing score, SAT reading score, and the number of people who actually took the test from their school. And then we used that to determine a person's SAT math score. So that was regression. And we sort of showed regression through the linear regression algorithm. And next, like the last lecture, Jeff showed us classification. So classification was a process of assigning each data point to a predefined class. So one example of classification might be that let's say we're trying to predict if a particular animal is a cat, dog, or other. And what Jeff used was he used a particular individual scores on their homeworks, and I believe the amount of hours they studied, they used those two variables to determine if a student was going to pass or fail the test. And Jeff exemplified classification through an algorithm called logistic regression. All right, so now I think we're done with our recap of what we have done so far. So now that we have done that, let's move on to our third big subtopic of machine learning, which is clustering. So what is clustering? So clustering is essentially the process of grouping certain data points together, ideally those sharing similar characteristics. So essentially what we're doing is for all our n observations, we're grouping them into some number of clusters based upon those that share similar characteristics. So for example, one thing you can do is one example, for example, is t-shirt sizes. That's the most common example of clustering. So essentially, we have a bunch of observations, a bunch of t-shirts, and our goal would be to cluster those t-shirts into small, medium, large, and extra large. So those will be our four clustering. And indeed, it turns out that this t-shirt clustering example is a very popular clustering example in machine learning. And as I said before, clustering is usually an unsupervised learning task. So far in regression and classification, we have dealt with supervised learning tasks. And essentially what those are is we're given a bunch of labeled data, and our goal is to generate the rule from our labeled data. However, in unsupervised learning and in clustering, you don't have labeled data. And essentially, you're trying to figure out a pattern. The model is essentially trying to figure out patterns in the data, and essentially they're trying to find similar characteristics. And then in clustering, at least, they're trying to group those similar characteristics together. All right, so that's what clustering is. And I guess in a more formal or more mathematical sense, clustering is essentially just given some number of data points, you're just trying to group them into k clusters. So that's what clustering is. And before we actually get started on an algorithm to actually cluster data points, let's think about the inputs and outputs of the algorithm. So the inputs are just n observations. So all the n observations and the value of k. And k is just the number of clusters. So in the typical case of clustering, you give the computer the number of observations and the value of k, which is just a number of clusters. And it turns out that not all clustering techniques require the number of clusters. So not all clustering techniques require the k value. For example, one very popular kind of clustering called hierarchical clustering doesn't involve the value of k. However, most traditional algorithms do indeed involve the value of k. So for our purposes, input, number of observations, value of k. Output. So what exactly are we going to have as our output? So for each observation n, so an output is going to be that for each observation n, we want to assign it a cluster label between 1 and k. Okay, so essentially, so this output means the same thing, basically it's the same thing as solving our problem statement. Okay, so now these are our input-output statements of our algorithm. All right, and one very popular algorithm used to solve this problem of clustering is called the k-means algorithm. Okay, so essentially, again, our goal of clustering would be given these 3 blobs of data. It's sort of to make to have a circle dividing these 3 blobs of data. Okay, and in our human eye, we can obviously this is pretty obvious to us. Well, these three are 3 very obvious clusters. But how can you have a computer, just have these 3 clusters like this? And using k-means, we'll get from this kind of data without the circles to data which does have the circles and sort of has the groups. Okay, so that's what k-means, the big picture of k-means is. So how exactly are we going to do k-means? So k-means is traditionally divided into 3 steps, or 3 steps usually. So our first step would be centroid initialization, and essentially what centroid initialization is that's our first step in k-means, and that is essentially initializing. It's initializing k points, and we call those k points cluster centroids. All right. So essentially, we want to initialize k random points from our data, and the value of the ith cluster centroid is called the mu sub I. All right. So that's what a centroid initialization is. And different initializations indeed might lead to different results. So if you recall from our discussion of gradient descent, we recall that different initializations, they have different results. So in the case of gradient descent, we fell into the local optima trap. And this also happens in k-means. So different initializations might lead to different results. And as in gradient descent, I guess the best way to combat this problem is to just run k-means a couple of times to actually see what you're getting. All right? And as I said before, we want to randomly initialize our k points. However, one very popular way to actually randomly initialize the points is to just pick our k cluster centroids as random data points, okay? So we essentially want to pick the k centroids as random data points in our actual data set. And all of this might actually seem really abstract. So why are we even doing centroid initialization? And to actually make this a lot nicer to see, I'll actually show you guys a visualization at the end of our discussion of the algorithm, which will hopefully simplify this algorithm quite a bit. Right, centroid initialization. Next is something called centroid assignment. All right, so centroid assignment is the following. So after we have initialized our centroid, our next goal is to give each data point a particular cluster, to basically assign each of the data points a particular cluster. And the way we'll do that is by computing the distance between each of the centroids and the point in the data set. So essentially, we'll take each data point and compute the distance between that and each of the 3 centroids, and whichever centroid value minimizes the distance, that's the centroid we have assigned our data point to. Okay, so that's essentially it for our centroid assignment step. And just a notational matter, we let C sub j, right over here, be the current cluster that the data point belongs to. So for example, if let's say we had 3 clusters, all right, let's say we had cluster 1, cluster 2, cluster 3. So if we had 3 cluster centroids, and let's say that cluster centroid 3 minimized our distance. All right, so let's say cluster centroid 3 minimize the distance between the centroid and the data point. Then we will have that. If let's say this is our first data point, then we have that for that particular example. So let's say the particular example is j. Then c sub j will be equal to 3. All right, and j is just what number data point it is. So if it's the first data point, it will have j equals 1, so on and so forth. Okay, so that's it for centroid assignment. Our next step is something called centroid movement. And essentially what centroid movement is after we have assigned a centroid value to each of the data points, what our next step will be to actually move our centroids from our random initialization. And how exactly are we going to do that? In particular, the way we do that is by moving our the particular way we move our centroids is by first seeing what data points each of our centroids possess, and then taking the mean of all the data points it currently possesses. For example, let's say that you have let's say that we have centroid 1, which currently possesses data points 1, 2, 2, 3, and let's see, 3, 4 maybe. Okay, so let's say that this centroid 1, let's say it possesses these 3 data points. And in particular, what we want to do is, in order to find its new location, we'll take the mean of all of these data points. So what we're going to do is we'll have 1 plus 3 plus 2, which is 6, divided by 3, so 2. So the 2, 2 plus 3 plus 4, which is 9, divided by 3 is 3. So after we perform centroid movement, our centroid 1 is going to move to coordinates 2, 3. Okay, and note that the centroid movement is independent of where the centroid where it actually started off with. Okay, so that's our next step, centroid movement, and we then repeat the centroid assignment, centroid movement steps until the process converges or the process stops. And essentially, and usually what that means is that we repeat this process until the value of c sub I doesn't change for all I. Okay, so that's it for our algorithm. So this is pretty much the algorithm. So what we do is we first initialize our centroids. So we initialize k centroid points, and then we assign each data point to a particular centroid. Then we move the centroids, and then we keep repeating this process until the algorithm converges. Okay? So one other detail. So here we said we computed the distance between each of the centroids and each of the points in the data set. You might be wondering, how exactly are we going to compute the distance between 2 points? Okay, and this is how we'll do it. So how do we compute distance? 1 second. So essentially the way we'll do that is, first I'll talk about how we can compute the distance in 2 dimensions, and then I'll move on from our example of 2 dimensions to our example of n dimensions. Okay, so first let's see how we can compute distance in 2 dimensions. So let's say we have coordinates p and coordinates q, and let's say p has coordinates x1, y1, and let's say q has coordinates x2, y2. So given those coordinate information, how can we compute the distance? And the way we do that is the following. So we generate a right triangle like this with PQ, I guess the segment PQ as the hypotenuse. And then what's the value of this? So if we call this point O, then I guess the segment, the value of PO, that's just x2 minus x1. And this value is just y2 minus y1. And thus, using the Pythagorean theorem, what you may have learned in geometry, PQ is just the square root of x2 minus x1 squared plus y2 minus y1 squared. So that's, I guess, your distance PQ. So now we have a formula of, I guess, given 2 coordinates, how we could compute the distance between those 2 points. And indeed, this notion of, I guess, this Pythagorean theorem notion, this extends to n dimensions. I won't prove this, but it does extend to n dimensions. So we have given two I guess vectors p and q, which have elements x1, x2, x3, xn, and vector q, which elements y1, y2, y3 up until yn. The distance between p and q is just x1 minus y1 squared plus x2 minus y2 squared plus x3 minus y3 squared, and on until xn minus yn squared. Okay, the square root. And we'll actually be implementing this distance algorithm technique. Okay. So now we're actually done with our entire algorithm. Okay. So now, as I promised, I'm now going to show you a very nice little visualization, which will hopefully make this concept a lot more clear. Will hopefully make things a lot less abstract, at least. So let me click on this. 1 second. So 1 second, guys. Can everyone see my screen okay? Dr. Willard, can you see my screen? Yes. All right, nice. Okay. Looks like, yeah. So now let's actually do this. So this is a very nice visualization.
Andreas, we're still seeing the presentation.
Oh, really? Okay, yeah. Let me change it real fast. New share. All right, how about now?
Looks good.
All right, nice. Thank you. Okay, so how to pick the initial centroids. So this is a very nice visualization that actually shows k-means very well in my opinion. So first let's ask us the question, how are we going to pick the initial centroids? And we're going to pick, so we usually want to pick them randomly, but in this case, I'll say that I will choose mostly because a lot of the times with this application, we might get very lucky, and if you get very lucky, this actually won't work very well. So I'm going to choose, although in reality, we're going to randomly do it. So this is our data set, and just looking at it, this is pretty. There's three very obvious clusters, one cluster here, one cluster here, one cluster here. And we want to use k-means to actually get these clusters. So let's start that. So we know that our k value is 3. So we first start with three random centroids. So let's say this is 1, and this is 1. So we have 3 random centroid values. So our next step, as before, is centroid assignment. So we can compute the distance between each of these data points and the 3 centroids. Okay, we compute this distance using what I have discussed before. We compute this distance, and then we find which centroid minimizes the distance. So, for example, just looking at it visually, you can see that this one right over here, this data point. This data point has the smallest distance between here and here. So this will get assigned to the blue one. And we do this for every single other data point as well. So let's click go. So now it does what I just said. So it just does the distance computation and the assignment. So our next step is updating the centroids. And that's essentially centroid movement. So we take each of these values, and then we move this to the mean of all the values it possesses, right? So for example, this centroid, this possesses all of these values. So we just take the mean of all the values it possesses. Let's update the centroid. Again, it moves. And then we keep iterating the same process over and over again. So we can reassign the data points, update the centroids, reassign data points, update centroids, reassign data points, update centroids, and it looks like it has converged, okay? And it converged quite fast just because these clusters are just very, very separable. And now we can see that we have 3 clusters that the model is clustered. Okay, so you have these 3 obvious clusters. So that's it for our visualization. And if you have any questions, please you feel free to ask the questions in the chat, or if you want to ask me directly, please ask it after. I'll have a time for question and answers at the end. Okay. So now we're done with our visualization. However, as promised in the Google Classroom, let's now go to the programming. And as we have done in our other examples, in our other lectures, programming isn't mandatory, but it's highly recommended. Okay. And I'll be actually implementing k-means in a programming in Octave. Okay, so we have used Octave in the past, so we're going to use Octave here. Okay. And so before we actually get started on programming, let's first look at our data set. Right, so I have the data set in Excel here.
Hey, Shreyas, we're still looking at the visualization.
Oh, really? Okay, let me change it. Okay, thank you for pointing that out. So new share, and let me go to how about now? Dr. Willard, can you see my Excel screen?
Yes, I can see it now.
All right, nice, thank you. All right, okay. So we have, okay, so now let's actually first look at our data set. So far, at least in all the visualizations or whatnot, you might not have actually seen the need for k-means. That is like you had these obvious clusters that any human eye could have detected. However, this example will really show you the power of k-means or clustering in general. So let's say you have 200 observations. So this is actually the example of customer segmentation. So you have 200 of these observations, okay, and 200 of these customer observations. And our goal is to sort of segment this data set into k clusters. Okay, so we have 200 of these observations that we want to and we want to segment them into k different clusters. Okay, so, and one reason we might do this is maybe we'll give different marketing, or we'll recommend them different products to each different groups. Okay, so that's actually why we might want to do this. So we have these three columns right over here, and I haven't actually labeled them. I didn't actually put a name of them, so let me actually explain what each of these columns mean. All right, so column A. Column A is essentially the age of the customer. So in this case, this customer is of age 19. Column B. Column B is just this customer's annual income in thousands of dollars. Okay, so that's just this customer's annual income. And column C is just copyright symbol. Okay, column C is just there's something called their spending index. And essentially what their spending index is just how much this particular customer spends on their products. So 100 is when the customer spends the most, and 1 is when the customer spends the least. Okay, and our goal will be sort of to cluster these 200 do 200 observations into k number of clusters. Okay, so now let's actually get started on programming. So let's go to our IDE. So I'm using the Atom IDE to actually implement this problem. And Atom is just just a basic IDE. It's basic IDE. You write code and then you can just run it. Okay. So first, now let's get started. So I've already written this before, but our first step will be to actually load our data set. So first step is to load our cutsegment data.csv dataset. All right. So now we have loaded the dataset into Octave. Our next step will be to sort of define the value of k. And we usually pick the value of k based upon our past experience with this topic. However, I don't really have much experience with customer segmentation, so I'll pick a pretty reasonable guess, k equals 3. And for those of you wondering on more optimal values on picking k, there do exist many more optimal values, and a quick Google search should yield many different techniques to actually pick the value of k. Okay, so now, but I'll pick k equals 3. So our next thing would be sort of define the number of observations. Let's have a variable to actually determine the number of observations. So let's call this variable num observations. And we have the number of observations. In this case, manually we have 200 observations. However, it would be nice if this code could be general, could be used in many different scenarios when the data set isn't of size 200. So for this, I'll be using the size attribute. So essentially, this number of observations is just the number of rows in this table X, in our data set X. And essentially, to find the number of rows, we use the size x, 1 attribute. Size x, 1 function, I guess, okay? So size x, 1, that finds the number of rows in the data set X. Size x, 2 would find the number of columns in the data set. All right? So next, if you go back to the PowerPoint, recall that our next step will be to sort of define the CJ vector. So we can actually store the current cluster that the data point belongs to. Okay, so next let's create the C vector. And let's initialize it to be all zeros with 200 rows and 1 column. Okay. Yeah. So one last thing before we move on is centroid initialization. So now let's initialize our centroids. Our centroids. So essentially, what we want to do is for our k is to just initialize k random points to serve as centroids. And since k equals 3, in this case, we'll have 3 centroids. So we have for 1 all the way up until k. All right. We'll have our ith centroid. And to be equal, okay. So now we have this code for our ith centroid. But how exactly are we going to pick our random values? And as I said in the lecture, one way we can do that is by just picking just k random data points in the actual data set. And one way we can do that is by just picking a random number between 1 and 200 and assigning that value and assigning the corresponding x value to our centroid. Okay, so let's do that. So first, let's pick a random number between 1 and 200. So first, let's use this range function. And range essentially just picks this uniformly a random number between 0 and 1. Okay. Now let's multiply that by a number of observations. Okay. So now we will get a number between 0 and 200. Well, yeah, 0 and 200. And then we will take the floor of this. And essentially the reason we take the floor of this is that the number of observations times rand, that can be a decimal number, right? But since we don't want it to be a decimal number, let's round down. We need to make it an integer, and then we'll make the integers by just rounding down to decimal. Okay, and next we will have x of this. Okay, so this is sort of the way we initialize our centroids. So let's end our for loop. So that's it for our initializations. But before we actually move on, let's just see if our program is working okay. See, I think I've octave already. Yeah. So all right. So let's just see if it's working okay. Let's just run this one time. This is called programming k-means.
You just called it programming means.
Oh, sorry. Never mind. Okay. Programming means. Okay. All right. So now we have actually done so. We actually look at what we have gotten. Okay. So this is our C vector. We have our number of observations in our actual data set X. Actual data set X. Let's see what else we have. We have our centroid vector here too. And one thing that might annoy you guys is why are they showing all the computation? Okay, so that's an annoying problem in Octave. And essentially the way we do that is by just giving it a semicolon at the end, okay? So that just doesn't show the computation. All right, so let me just try to comment. So this is, lines 1 to 7 are for initialization.
Shreyas, sorry to interrupt you. There's just one tiny bug here.
Oh yeah, I know 0.
Yeah. So do you want to talk about the difference between Python and MATLAB in terms of their indexing?
Yeah. So one thing that Jeff pointed out here is that this could indeed give us 0. Okay. So for example, so one thing about this is that this floor of number of observations times rand, that gives a random value between 0 and I believe 200. Okay. However, indexing in Octave starts from 1 up until 200. So 1 up until 200. So this isn't that big of a deal, but that's one thing that might happen. And I guess as an exercise, you can just see how you can combat this problem to actually get it from 1 to 200. So that was actually an exercise I was going to give them. All right. Okay. Yeah. So now, yeah.
Sorry to interrupt.
Yeah, that's fine. That's completely okay. Okay. So now we have this done. So now let's do our next step, which is centroid assignment. Okay. So next step will be centroid assignment. And essentially so in order to do centroid assignment, which is essentially computing the distance between each of the data points and the 3 centroids, essentially in order to do that, we need to first define a distance function. Okay. And I've already written a distance function beforehand called distance. All right. Okay, so let's have this right over here. So I already created the distance function beforehand, and I encourage all of you guys to look over it and sort of just see see how the distance function corresponds to the distance that we learned in the lecture. Okay, so that's the distance function I wrote. And because we probably won't have time to just write the distance function here. So now let's actually do centroid assignment with the distance function we have. Okay. So we have, so now let's do centroid assignment. Essentially what that is, for all I from 1 all the way to your number of observations, okay? So for all I from 1 to number of observations, we want to essentially find which centroid minimizes the distance between that observation and each of the 3 centroids, okay? So the way we'll do that is by creating some distance vector, which just has what each of those 3 distances are from the data point to the centroid, and then actually finding which centroid minimizes that. So let's actually do that. So we want to have 3 distances: 1 distance, 2 distance, and 3 distance. Okay. And now I haven't filled in the parameters, but essentially what the parameters are is the first parameter is from the ith training example all the way to let's see, the first centroid. So we're going to compute the first centroid distance. Next will be from our ith centroid to our second centroid distance. And the next will be from our ith centroid again. I'm sorry, our ith data point again, sorry, to our third centroid. I'm sorry, the zoom set centroid here. Right. So we have the distance vector. And essentially what we want to do, and so I'll be writing this code and I'll explain what this means in just a second. So essentially what this is so now what we do is minimize this distance vector. So find which of these three sort of distances are the smallest, and then and we evaluated the smallest, and then we put the actual distance in the dummy variable. This isn't of importance to us, but what is of importance to us is the value of c sub I. So essentially, what the index of the minimum is, we put that in c sub I. So for example, if the third centroid minimized the distance, then we put c sub I to be equal to 3. So just to make sure everything was working okay, let us just 1 second. Yeah, let us just run this again. Okay. So it says for I equals 1 to the number of observations. 1 second, guys. Let me just run this one more time. All right. So it looks like we have some kind of error here. It's probably the syntax error here.
Trace, I think it's the colon after the number of observations.
Oh yes, correct. See, okay, I'm just too used to Python. Yeah. So okay, it turns out that in Python you do put the colon after the for loop, but in Octave you don't. All right. So now this should work if you run it one more time here. And okay, so now it's essentially just doing all of these computations, and we get our C vector, as you can see here. Okay. But as I said before, the computations might just be very what's it called? Just very annoying. So let me just semicolon them so we don't show the computation. So now we're done with distance assignment. And thank you, Shraman, for pointing out the error here. All right. So our next one will be centroid movement. And the way we'll do that is the following. So we'll have so essentially what that is we just take each of we essentially take each of our centroids and see what points the centroids are assigned to, and then sort of take the mean of all those points. Okay. Let's do that. So we'll have for I equals 1 all the way to k, we'll have let's have this index vector. So I'll explain what this means in just a second. So essentially what we'll have is create an index vector whenever the c equals I, and then whenever c equals I, we want to find what the corresponding x value is for that index, and then sort of take the mean of that. Okay. So now we'll have our ith centroid right over here, just to be the mean value of our x of our index. Okay. So now this essentially takes this code essentially just takes all the data points it possesses and takes the mean of them, and does just moving the centroid. Okay. Nice. So now we're done with our distance movement and distance assignment. So we're done with our assignment and movement step. But we want to keep doing this until we converge. However, I'm not going to write code to actually do this until we converge. Instead, what I'm going to do is just run it 100 times. Run it about 100 times until when? That's probably a very reasonable, just a reasonable number of iterations until it converges. And I really recommend all of you guys to write code to do this until it actually converges. Okay, so that's what I recommend you guys do as an exercise. So, and after I finish writing this and after finish this lecture, I'll give you some. Well, this isn't mandatory, but just some optional exercises so you can get a better feel for the code. Okay. All right. It looks good. Let's run this again. Hopefully we don't have no errors before. So now we essentially are running it. Okay. And as before, it's showing us all the computation just because we forgot to put the semicolon, but that should be okay. Let's just wait for some time to actually get our results. So now you may be wondering, this algorithm, at least my implementation of this algorithm, takes a lot of time. And there exist many different ways to actually implement this quite a bit better. So one way you can do this is, instead of using many for loops, as you can see, I can already count like 4 for loops, okay? Instead of using these for loops, one thing you can do is something called vectorization of code. Okay, so actually when you vectorize code, this algorithm works a lot faster. And in general, in machine learning, vectorizing code is very important. But in my opinion, vectorizing code makes it a little bit, it just makes the implementation a bit unintuitive maybe. That's why I'm not doing it here, okay? So let's just wait for some time. Hopefully it's finished running. Yeah, this is actually quite, let's wait for some time. So it's running 100 times, it's taking quite some time here. So for now, 1 second, let me just actually terminate this. And let me go back here. Let's see. Yeah, we just run it here. All right, 1 second, guys. Yeah, so I'm going back to my, it says community AI. See, I've saved this in the community AI drive. 1 second, everyone. Okay. Not too sure why this is happening here. But okay, but when we run this, we should get in results. But just 1 second, guys. I'm not sure why my folder isn't working well. Let's see, Dropbox / AI. Okay. All right. I'm not too sure why exactly this isn't coming here. All right, so I'm not too sure why that was happening, but let's just now that we're here, let's just comment. Let's just have a semicolon here, just so our computation isn't very annoying. Have a semicolon. Let's go back here and let's actually run this one more time. So this is called programming needs. Now instead of showing the annoying computation, it's just taking time. It's not being not just showing all the annoying computation. So let's just wait for some time until this runs. Okay. In that meantime, let me actually answer some questions from the chat. Looks like we have 19 questions. It says, will there be a Python programming?
I think you again put. Oh, actually, never mind.
All right, take it. Yeah. So it says, will there be a Python programming example for the k-means algorithm? Okay, so I'm not planning on actually doing giving a Python programming example, but I guess if you want to after the lecture, I could implement this in Python and share the code if you want me to. Okay.
Chris, I already said that I would put one together.
Oh, okay, yeah, that's fine too. Jeff could do that as well. Thank you. All right, yeah, it looks like it has run. I think we have forgotten to display the actual C vector, but hopefully you guys are convinced that this actually works, okay? Yeah, we forgot to display C, but I think that's fine. But now, even that you have seen, after you have run this, and even when you see the C vector, while that might be okay for some of you guys, a better way to actually like look at this result is by plotting the result, okay? And so let's actually plot this, and let's actually plot this. And if you actually go back to our Excel here, we see that we have 3 dimensions of data. So column A, column B, and column C. However, one thing that you might, however, while it's very possible to graph in 3 dimensions, it's in my opinion a lot messier. So let's just focus on the first 2 dimensions when we graph. Okay, let's just try to graph these first 2 dimensions right over here. So let's do that. So our goal is essentially just to graph the first 2 dimensions and see what cluster each of those belongs to. Okay, so we'll have, let's plot whenever x. Let's see. Yeah, so essentially what we're doing is we're seeing whenever our x belongs to our first cluster, okay? Whenever it belongs to the first cluster, and then we'll give it sort of a green data. We'll denote that cluster as a green point, okay? So now let's hold on, sorry. Okay, so let's just hold on to this as before. So now let's again plot. Let us plot when C belongs to the second cluster. Okay, when C equals 2. Not sure why I did that. Okay, plot when C equals 2, and then yeah. So we're going to plot its first dimensions and its second dimension. Okay, and let's give it a red color maybe. Okay, so R means that we're giving it a red color. I think it was okay. Let's again hold on. Do that. So we'll have plot. Let's plot when x when C equals 3. Okay, have when C equals 3. We'll do the same thing. We'll plot the first dimension and second dimension, and let's give it a blue color. Okay, so now we're actually done with this. So now when we actually run this, we'll get a nice little graph that you can look at, and maybe. So if you're trying to actually show this to someone, you can this graph will help in presentation. Okay. So now let's wait for some time for this to run. And I do realize that that especially the programming thing, I might have jammed in a lot of information at you guys once. So as I said before, I encourage watching the recording just a couple of times so you can get a better feel of this algorithm in general. This is actually very interesting. This is one of my favorite algorithms, k-means, just because this is actually a really cool algorithm. I really like it. So just watch the recording a couple of times so you actually get a better understanding of the algorithm. And we'll be posting the recording on Google Classroom. So let's still wait for some time. Okay. Ooh, this is taking quite some time to run. All right, Trace. Is it possible to go back to the start of the code and go through it? Got lost in some of the syntax and code. Maybe after you finish it with all the code. Yeah, sure. Yeah, Rishi, I can definitely do that. Yeah, it does. I think I might have actually forgotten. I might have explained all the syntax very well. So let's actually start with the beginning. So first is x equals load the actual customer segmentation over. Wow, yeah. So this is sort of our but here, I'll talk about this graph after I finish. So this is the graph we actually get when we do this. So just from here, we see that this is maybe one cluster. This is another cluster, and this is another cluster. And just from looking at it, it looks like k equals 2. That might have been a better suit than k equals 1. k equals 3, okay, just from looking at this. However, k equals 3 is pretty good. And it turns out if we run the algorithm again, we're most likely going to get a slightly different cluster, okay? So let me go back. So now let me actually explain the code again from the beginning without actually typing or whatnot. So first, x equals load customer segmentation data. So that's essentially just loading the customer segmentation data set into Octave. Next is k equals 3. And k equals 3 is just, that's just a variable, so that's k is the number of clusters. So we have number of clusters right over here equals 3. So now we have the number of observations equals size x comma 1. And essentially what that is that size x comma 1 just measures the number of rows in the x data set, okay? And the number of rows is just the number of observations, right? So size x comma 1, that's just the number of rows. Size x comma 2 is the number of columns. So in this case, we want a number of rows, so we have size x comma 1. So next, we initialize the c vector. And the c vector is essentially just, it's just a vector which has what each of the data point, which centroid each of the data points are assigned to. And we start off by sort of just having c to be a zero vector, 200 by 1 0 vector, meaning that it just has all zeros in all of its positions. Okay. So next this step is centroid initialization step. Okay. So this next piece of code is centroid initialization. So now we moved on to centroid assignment, okay? Centroid assignment right over here. And it turned out centroid assignment. And in order to actually do centroid assignment, we want to first create a function which takes two vectors and computes the distance. And I talked about how we can do that in the lecture, but this is sort of this is a code to actually, this is a pretty good code to actually compute the distance between those two vectors, okay? And as an exercise, I encourage you guys to just go over it, just go in your own time, just look at the distance code and see how this relates to what we learned in the lecture. So next we have this. So for this section right over here, this is sort of the centroid assignment. This is our centroid assignment. So for each data point, this essentially assigns it to a particular centroid. Okay. So now this piece of code, this is the centroid movement step, and this essentially moves the centroid. Essentially moves the centroid based upon what point it possesses. Okay, and then we keep doing this 100 times. Although in an optimal scenario, you want to keep doing it until you converge. Although 100 seems like it's a pretty reasonable amount. Okay. So next, this figure thing right over here. This just measures. This is just So this is essentially just plotting the data, okay? And plotting the data to see which cluster it belongs to. And actually, next time, what I might do is based upon your preferences, I might just write this code up ahead of time instead of actually showing it. Well, my idea behind showing it was that this might make it more intuitive. But if you guys just want me to go over the code like this, I can do that as well. All right. So hopefully that was Rishi. Is that a good? Is that sufficient, or do you have any more questions on the code?
I think that was a good example. So for some of the terms that you use, like distance and centroid, are those already built into Octave?
No. So essentially, okay. So I created this distance function. Okay. So I created this function ahead of time called distance x comma y. So this is essentially a distance function, which takes in two vectors, x and y, and computes the distance. So distance isn't an inbuilt function. And I initialized centroids from the beginning. It isn't, although it might seem because of its color that it's inbuilt, it's actually not. Okay? Is that a good example? Is that a good explanation?
Okay, and inside the centroid function, so where it says I comma colon, so it means it goes to like what does it go to then?
Oh, that's a great question. Okay. Yeah. So I actually haven't talked about that. So that's Octave syntax. So essentially what I comma colon is, so centroid 1 comma colon, that just outputs the first row of the centroid matrix. So are you familiar with what a matrix is?
Yeah, I know a little bit about matrices.
Yeah, so for our example, just think about matrix. It's just a table of values, okay? So centroid 1 comma colon, it essentially just finds the first row of a matrix. So let me actually do that here. This might make a lot more sense. So let me first initialize. So this is our X matrix, okay? So this is sort of our matrix. It has 2 rows and 4 columns.
Okay.
And what X1 comma colon would do is we'll just find the first row, okay, of our X matrix. And what X colon comma 1 would do, it would find the first sort of first column, okay?
Okay.
Yeah, so that's essentially what that is. Any more questions? Those are really good questions. I really like them.
That should be it. And okay, so with at the end where we iterated through the code about like 100 times,
Yeah.
so J is just like it just tells you what iteration you're on, right?
Yeah, exactly. So so essentially the only reason I do this is so I can repeat this process 100 times. And indeed, J does. It's just J's what number iteration you're on. Exactly.
Okay. Okay.
Any more questions?
No, that should be good.
All right. Thank you. Thank you for the questions. They're really good. Any more questions? Yeah. So would you guys maybe want to see the C vector? Yeah. So any more questions maybe related to just the algorithm in general?
Oh wait, Shreyas?
Yeah.
What would you call the cost function for k-means?
Oh, that's a great question. Okay, so k-means does have a cost function. So essentially what the cost function is we're trying to minimize the distance between each of the data points and the cluster mean and the cluster centroid that it's assigned to. So that's what so it's essentially the distance between each of the data points and the cluster centroid it's assigned to. Okay, is that sufficient?
So by that, do you like, because the cluster centroid has to like minimize the distances for like all the points. So like how does that work in sync?
Okay, so essentially, so when I actually implemented this algorithm, I didn't use that cost function at all. Okay. However, one other way you can do that is instead of doing, I guess, this reassigning, and then moving, instead of doing that, you can just minimize that cost function that I said before. So one thing that people actually do is instead, in order to check if this algorithm is going well, is to actually implement this in a different way, where instead of doing this step right over here, we minimize the cost function. Okay, so was one way. Was that the question you were asking? Because I might have misinterpreted it.
Like, yeah, that was good, but like what is there like a specific equation which like has like variables that work together?
Yes, exactly. Yeah, there is, and so it's very difficult for me to actually write that equation in the chat. However, let me actually just so essentially it's just the distance. So it's a distance between the observation and the cluster centroid. So let me actually look at so here, let me Google it for you can actually look at the cost function. Okay, k-mean cost function. Yeah, so this is the cost function.
Okay.
Yeah. So essentially, what this is so x. So what this is here. Maybe this is a better. Oh, sorry. Okay. 1 second. So what essentially this is that the cost function is just a distance between the particular observation and I guess the and then the centroid it's and the cluster centroid is assigned to. So this is the equation for the cost function.
Oh.
And ignore this xi, this weird belonging symbol. So that's not very relevant in this case.
Okay. So it's almost like a least squares.
Yeah, it's very Yeah, it's very similar to least squares. Yeah.
Okay. Okay. That's
Oh
good.
yeah, exactly. Yeah. So k nearest neighbors and k yeah. And it turns out, so I think I think might have confused some people is that wait, did we write that? Well, yeah. So this is a k means actually. Any other questions? And also, yeah, Arona, this lecture focused on k-means. So while k-means and k-n, while they might just sound similar, they're completely different algorithms. So k-n is a regression technique, and k-means is a clustering technique. Okay. Any more questions regarding this? All right, okay. When will we begin working on the final project? Okay, that's a great question. So Rishi, so you can start working on a final project right now. So essentially in the final project, you don't have to actually build a project. For now, you just have to sort of present your idea and how you're planning on implementing the project, okay? And you can begin starting right now if you want to. Yeah, so essentially use what you learned in the lectures to actually do the final project. So you can start right now. Is that, yeah. Okay, but will we have a session? Oh wait, what exactly do you mean by that? Rishi? Rishi. Oh, like a class. So currently we are thinking of having a class for the final project. It's just something we're planning on doing independently. But if there's enough interest, sure, we can do a class where we can explain the rubric or whatnot. Yeah, that's completely fine. Yeah. Yeah, you can. Right, no problem. No problem, everyone. See you guys later. Yeah. So next lecture we'll actually be discussing artificial neural networks. So me and Jeff are going to teach artificial neural networks, which might actually be one of the most state-of-the-art technique we're going to cover in this lecture. So stay tuned for that. All right. With that being said, bye guys.